Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, good morning everyone. So today, this is our first lecture this semester. Make sure that you are sitting in the correct classroom. This is for FINM7003 or 7003 Continuous Time Finance. So, first, in the first lecture, I first want to welcome everyone to this class because I know that the past summer break has been very special for everyone, and we experienced lots of challenges. And unfortunately, still there are quite a few students now because of the travel ban cannot be on campus, so they will enter through the remote class mode. And so I'm very happy to see you today, and I hope you enjoy this course throughout this semester. So firstly, I want to have a self-introduction. If you haven't taken my course before, my name is Fei Huang, and I'm currently a senior lecturer in actuarial studies in the School of Finance, Actuarial Studies, and Statistics. So this will be the third time teaching the continuous time finance at NU, and possibly the last time. I hope you enjoy this course. Well, so firstly, if this is a compulsory course for you, either you are in a quantitative finance major or an actuarial major, then it's possible that this is a compulsory course. So I expect that you learned the useful techniques that will help you for your future career. If this is an optional course, I want you to have a double think before you truly get enrolled, because this will be a relatively technical course. We will use lots of mathematics, probabilities, statistics. You will face lots of mathematical proofs, derivations. So if it's optional and you are not very comfortable with that side, then have another think. Right? So first, maybe I'll do a little survey so that we understand each other better. So how many of you are in the actuarial discipline? The majority. Thank you. So how many of you are in the quantitative finance major? Quantitative finance. Thank you. Okay. How many of you are choosing this as an optional course? Nobody. Okay. Good. So if you have any question about this course, feel free to come to make contact with me. So here, I opened up the Water page for you. So everything about this course you can find from this Water page. So I suggest you to log on to it frequently to check the latest material or announcements. So on the right-hand side, there's a block which is about me. And you can see that here, I want to especially remind you that the consultation hours is a little bit different from what is listed in the course summary. So the updated consultation hours will be from 2:30 to 4:30 on Wednesdays. But I understand that this may not be an ideal time for everyone. So you can see me by making other appointments or simply stop by my office when my door is open. So basically, when my door is open, that means I'm happy to take questions whenever you have. You can just knock on the door and come in. If my door is closed, that means I probably was having a Skype meeting, or I may not be in my office. Right. So, but I will make sure that my office will be the door of my office will be open most of the time. And so my office is in room 3.10. It's on the third level of the building 26C, which is within the College of Business and Economics. And the tutor's information, so we have just finalized the tutor. For the on-campus offering, you will only have one tutor, which is called Michael Robert. And Michael has already achieved a PhD in mathematical finance. So he knows this discipline very well, and I'm very happy that he will be a tutor of this course this semester. He will be a tutor for both undergraduate and postgraduate. Later on, I will post a tutor's consultation hours for your information. And here we have the tutor. Here we have tutorial enrollment. Please make sure that you sign up a tutorial before the due date, which is Friday this week. Make sure you sign up your tutorials. And the tutorials will start from next week. Okay. And then you can find out all your recordings here on this Wharton web page too. And here in the course resources section, I post the practice exam question and solutions. So it will not be used for now. It will only be used for maybe in week 11 or week 12 after we have started almost all the materials. Then you can do the practice exam to have a mock exam before the final. And then I also posted the formula sheet, standard normal table for your information. So these two will be provided during the final exam. Okay, so you can familiarize yourself with the formula sheet and standard normal table, so you don't have to memorize any of those that's listed here. They will be provided to you. And for this course, everyone will get the same formula sheet, no cheat sheets. Okay, so everyone got the same formula sheets. And another thing that I posted here in the resources is an undergraduate guide to R. So the reason is that although this course, we won't have a software or program section in the final exam, but we do encourage you to have some, practical skills so that you know how to apply the model in reality, not just understanding theories, but also have knowledge of how to apply them in practice using the software. So the software I recommend here is including both Excel and R. So here, but I did not provide a guide to Excel because I assume that most of you, or maybe every one of you, have already got some exposure to Excel, which doesn't really need a guide to teach you how to use Excel. And I assume that some of the previous courses probably have already taught you how to use Excel to solve some questions. And here, the only thing I provide is an undergraduate guide to R to those who who is a newbie to R and haven't really got an experience with R. So this is really an introductory level guide. If you already have a significant amount of knowledge of using R, then you don't have to read it. But it may still be useful if you forgot something, say how to import data or how to say save a file or set up a working directory, then you can still use that as a guidebook to remind you of something. So this is, you may want to start learning it when you have time, because later on, for one of the tutorials, we do have an R-based and Excel-based question that we will teach you how to use R. And for one of the assignment questions, we may also design an assignment question that's related to using the software to solve it. But I guarantee that there will be no question related to R in the final exam. It's only been either in the tutorial or one question in the assignments. Okay, I think another advantage of introducing the software is to provide you with a bit more motivation. Right? Sometimes learning pure mathematical proof and theories will be a bit boring, but if you understand how to apply them, it may appear to be a bit more interesting. So hopefully this can also provide you with a bit more motivation, make this course a little bit more interesting. And for assessments, I'd better open up the course summary to look at it. So here I posted two versions of the class summaries, one for undergraduate, one for postgraduate. But they are almost the same. So the postgraduate version, the final exam will be different. I mean, one question. There will be a difference in one question. But the course offering, the contents will be the same. Okay. Here, I open up the class summary. So you can see that here we can find out the learning outcomes of this course. So continuous time finance is really to provide an introduction to the theory and the practice of derivative pricing and hedging. And the aim of this course is to provide students with the mathematical skills needed for the valuation of derivatives. focus will be on the application of results rather than their mathematical derivation. And these tools will be applied to derive the famous Black-Scholes formula to price options on currencies and interest rate derivatives. So this is a basic summary of what we will learn. So for this course, there will also be some outcomes here. So it's like communicate the basics of stochastic interest rate models and use them to evaluate simple cash flow models. So the first outcome was actually, it used to be in the financial math, but from last year it moved to CTF. It's mainly to be consistent with the requirements of the Actuaries Institute because due to the change of the syllabus. But this is really only a very small proportion of this course. So it will appear in week 11. We will have this part added. And then the other two outcomes is like use upcharge-free approach to pricing. This is really the core pricing approach, which we will spend a large amount of time talking about that. And then we will discuss how to use mathematical tools to price derivatives, such as Ito's lemma, martingales, stochastic differential equations, change of measure, and the martingale representation theorem. And I will leave it to you to read the policies and some other sections. I will just briefly go through the most important part. So for the required resources, I think that we do have a prescribed textbook, which is the options, futures, and other derivatives, the global edition. Make sure it's a global edition. You can use either the 8th edition or the most recent 9th edition. It's all fine. So I think the university bookstore should have some storage for this textbook. I also make sure that in the library, they also have this textbook have been put in the 2 hours loan section. So this will be a useful textbook. And this is, in any case, this is a very popular and very famous book, especially if you major in, say, quantitative finance or actuarial studies. If you want to go along the direction of finance or investment-related career path in the future, then this is almost a must-have book. This is a very important book for derivatives pricing. But we will not cover everything in this book. We will only cover part of it. And for those students majoring in quantitative finance, there will be another course called Advanced Derivatives Pricing in the second semester. And that course, as far as I know, it will also use this book as an important resource. So this book can serve as for both courses. There are also some other recommended resources. For example, the Steve Straff's book, Stochastic Calculus for Finance. This is also a very important book for especially, say, bankers, investment bankers on the Wall Street. So it actually have 2 volumes. Here, we only list the first volume, the binomial asset pricing model. And the second volume will be the continuous time finance. So here, the first volume we listed here will be mainly used for understanding the using binomial tree method for asset pricing, for option pricing especially. So this book will be especially used for week 3, when we talk about the discrete model. And another textbook is Financial Calculus by Baxter and Rennie. So this is a actually very thin book, but covers almost everything that's from from derivatives pricing to hedging, risk management, and interest rate derivatives. So this is a thin book, but it covers lots of interesting sections. So these are the recommended resources. They are also in the library, and I also put them on the 2 hours loan section for you to borrow. And for the feedback, so for the feedback thing, I think I really appreciate if you have any feedback for this course. Feel free to let me know, either by sending me an email, or you can simply post a notice on Wordle, or just let me know in person. I appreciate if you have any feedback. Say whether the class is too difficult, too easy, the path is, say, too slow or too fast, so just let me know. On the other hand, I will try to provide you with feedback as much as possible. So for example, in your assignments, of course, we will have markers marking them. We will make sure to provide you with comments so that you understand where are the weak points and where are the content that you are not very good at. On the other hand, I will also be very happy to provide you with individual feedback if you prefer to come and see me, say, express your concerns or say how you feel about this course. I'll be happy to provide you with feedback if you want to consult with me. And then the next thing is the assessments. I know that's the thing that you care about most. So for the assessment requirements, let's jump into the assessment summary. So for the on-campus offering, we will have online quizzes, assignment 1, assignment 2, and the final exam. So the online quizzes will have 2 online quizzes, one in the first half, one in the second half. So you can see where are the due date and the return date. So for the online quizzes one, basically we will have a question bank, and you will be allocated 1 hour to complete around 10 questions. And you will get the solution right after you submit your results. You can get the feedback immediately. So the requirement is that everyone should do these online quizzes all by yourself without discussing with the other students. And also, we have a relatively large question bank, so everyone will get a different questions, but the questions will be similar in style. Similar in the difficulty level. So everyone will be different. So, but although it's a question bank based quizzes, I require that you should not release the quizzes to the other students. Okay, you only focus on your own questions and for the online quizzes and complete it all by yourself. So each quiz counts 2.5%, and in total they count 5%. Assignment 1, assignment 2, this will be, so for the online quizzes, it's all multiple choices questions, around 10, and you will be allocated 1 hour. It's all calculation based. You can calculate a number and you select which one is correct from 4 or 5 choices. And for the assignments one, it's be a combination of calculation and proof questions. So we require you to put down the steps very clearly one by one and show us how you solve this question. And for one of the assignments, we may have one of the questions related to the software, so that you will have to use software to solve it. So this is our 2 assignments. And all of these assessment items, quizzes, assignment 1, assignment 2, they are all redeemable. So that means in the final exam, if you did really bad in the quizzes or assignments, but you did really good in the final, that's all fine. We will basically calculate all the potential combinations of these assessments, and then find out the toppest one, the biggest one that you can get. If you did really good in the final exam, then 100% weight will be in your final exam. But if you did really good in the previous one, then relative weighting will be allocated in the previous assessment items. So the ideal of having this redeemable option is that I don't want you to cheat on any of these assignments, because I think it's be really good if you benefit from these exercises, right? It's really for your own benefit. So you can also see the learning outcome. So for the online quizzes, it will be focused on the maybe first 3 or 4 weeks lecture. I will put the exact coverage later on Wattle. I will tell you what are the exact coverage, how many weeks. And for assignment 1, assignment 2, one will be in the first half, one will be in the second half. So I will also let you know when it will be released and when it will be due later. So all the specific information will be announced in class and also on the Wattle discussion or the course announcement forum. And for the final exam, it will be a closed book final exam, centrally timetabled. So we don't know the time yet, but it will be a closed book exam. All you can bring in is a calculator and a dictionary if you want. But the formula sheet and standard normal table will be provided by the invigilator. Okay, so you can read the details of these assignments in the course summary. And all your assignments, the quizzes will have to be completed in the online. Later on, we will have an online quiz function on Wordle, so you can complete that online. And for the assignments, you have to submit it electronically via the Turnitin, which we will also have an assignment submission function on Wordle. So it's all electronic, no hard copy submission. And there will be no late submission allowed. And for the returning of the assignment, we will it will be announced on Wordle when it will be returned. It will be in week 7 and week 12. And no, it's not permitted for a resubmission of assignments. Okay, I will leave it to you to read the other more generic items. That's very general, applicable to all the courses. So the specific related to this course, the stuff that I have already presented. Any questions so far? If you have any questions regarding the course outline, just let me know. Okay. And on this Wordle web page, you will see that for each week, we will post the lecture notes. The lecture notes, you can see the date is due 2019, but it's actually 2020. So because the lecture notes is exactly the same as last year, so I just use the same lecture notes for this year. They will cover the content. As I mentioned before, there was a change of syllabus from last year, but it will remain the same for this year. So for the offering of this course, we will give you these lecture notes. You can refer to all the lecture notes in the 11 weeks, first 11 weeks. So for the delivery of this course, I prefer to use a document camera. The reason is that this course is relatively technical. So I think the thought process is much more important than the result. So I want to show you how this thought process is going on so that you can understand how, step by step, how to find out the solution or how to complete a proof. So I will use a document camera, and later on, after each class, I will scan my documents here, my handwritten notes, and you will have access to the handwritten notes later after this class. Okay. So and another thing about this, the good thing is that everything will be recorded too, so you don't need to worry about that. And tutorial questions and solutions will also be posted here. So you can see the tutorial 1 question is already on Wordle, so you can refer to that for the next week's tutorial. And the tutorial solution will be posted right after, maybe at the end of each week, after the tutorial has been delivered. Any question here? Okay, then I think we can start our lecture today. So for the lectures, it will all be in this law theater. So the Tuesday offering is from 11 to 1. It's a 2 hours lecture. We will have a 5 minutes break around 12. And Thursday's lecture, still in this classroom, is from 10 to 11. It's a 1 hour lecture. Okay, so this course, Continuous Time Finance. I know that at the beginning I said this will be a technical course. You can expect that there will be some mathematics, right? Some technical stuff. But I really hope that it's not it's not a very boring course, although it's very easy to make it a very boring course. But I still hope that you find some interesting parts from it. It will be very useful. Actually, it can be a very interesting, very useful course. So the title of the course is called Continuous Time Finance. Well, this is not exact, cannot reflect the exact coverage of this course. Actually, continuous time is something we will spend maybe 80% of the time on this topic. But still, there will be some discrete time finance or discrete time pricing. So, actually, this is more like this course will be, say, derivatives pricing and hedging. So that will be the main content. So in terms of derivatives, we will mainly focus on options. Options is really the main focus, but we will also discuss forwards, futures, and some, say, interest rate derivatives. Okay, so before we start this course, we understand that there are two prerequisites before entering this course. You have to complete the derivatives, right? Earlier course called derivatives, and also the introductory stochastic process. Right? So the reason is that the derivatives will provide the foundation for the domain knowledge, the context. Right? We are really talking about derivatives pricing. Well, the introductory stochastic process will provide the mathematical background, the mathematical foundation to learn this course. So we will use stochastic calculus, we will use Brownian motion, geometric Brownian motion a lot throughout the process. I understand that after taking a course, say last year or even earlier, you probably have forgotten some materials in that course. So we will make sure that we'll have some revisions for the previous courses. Okay, so as I mentioned before, this course is it's mainly about derivatives pricing. Then what's the difference between this course and the previous derivatives course? So the main difference is that in the previous course, you are only taught what is it, how to use it. But this course will tell you why is it, how to derive it. So this goes into a deeper aspect of the pricing, okay? So in the previous derivative course, you were only taught, okay, this is a Black-Scholes formula. What's the inputs and how to get the outputs? That's all. You were not told why is that, how to derive that, right? But in this course, we'll go much deeper to tell you why that and how is that. So the rationale behind this is that we want you to learn the thought process so that in reality and later, when you want to price a new contract or a new derivative, you know how to do it. So this will really teach you the tool how to price a derivative rather than just teach you, okay, this is a pricing formula, how to use it, but how to derive the pricing formula for the specific derivative. It can be, later on we'll discuss different derivatives, and you can even design your own derivative if you want, and then you can figure out how to derive the pricing formula for it. Okay? And in terms of derivatives pricing, so in the first lecture, I really want to give you a bigger picture of this course, not just talk derivatives pricing, but also put it in a more bigger background, say finance, right, or asset pricing. So let's put it very big. Derivatives pricing can be regarded as a special area in finance. I know that for those actuarial students don't feel that it's irrelevant to you. Actuarial studies really are interdisciplinary. It covers everything, finance, economics, statistics, mathematics, right? So finance is also closely linked to actuarial studies. Okay, so traditionally derivatives pricing is a finance area. Then for finance, it's really have two areas. One is called asset pricing. One is corporate finance. So for the asset pricing part, and derivatives pricing really belongs to asset pricing. So what is asset pricing? if you have learned some first-year courses like Foundations of Finance or Derivatives or some, say, investments, so if you have learned anything about finance, anything start with FINM, you probably will encounter something related to equities pricing, bonds valuation, or some terms like CAPM, APT, FAMA French, right? So they are all related to asset pricing. So for asset pricing, it's what are the assets? What's the definition of an asset? Or can you give me some examples of assets? I've already told you, right? Equities, the bonds, and of course, derivatives. They are all assets. So why they are called assets? Assets, if you want to give it definition, can be just a sequence of cash flows, right? That's the definition. No matter it's equities, bonds, or derivatives, they can all expect a sequence of cash flows into the future. And asset pricing is really to find out the value of the sequence of cash flows in the future, right? So this is asset pricing is really about find out the value of, say, cash flow 0, cash flow 1, cash flow n in the future. So that is asset pricing. Then what will affect the value of a sequence cash flows? There are mainly two factors. One is time. The other one is risk. Only these two. So that's why you have learned financial math, which is mainly to deal with a time effect, the time value of money. Today's dollar has a different, if it's $1 today and $1 tomorrow, it's different, right? You know that. There will be a discount rate should be applied to the tomorrow's $1 so that you can count, you can evaluate the today's value of tomorrow's $1. And the risk is a more challenging task. So it is really the risk make the finance, will make the asset pricing complicated but also interesting. So the time component is relatively easy to consider or to deal with, but risk is really the difficult part. So to deal with the risk, here we can classify the asset pricing into two methods. So basically, how can we do asset pricing? We know that in the financial markets, we have different assets. They can all be described as a sequence of cash flows. The how to price the value, there are basically two methods. The first method is called absolute pricing. And the other one is called relative pricing. What is the absolute pricing? Think about equities. Can you give me an asset pricing model for the equities? Example of asset pricing model. CAPM. It's called capital asset pricing model, right? This is just a very natural example. So basically for the CAPM framework, there's only one risk factor, which is systematic or the market risk. And another example is the APT or factor models, say FAMA French 3-factor model, then they give you 3 factors. So absolute pricing is like they really use the macroeconomic risks. They can identify what are the risk factors and then use it to quantify the return, the required rate of return, and then use that to do the pricing. So this is like use the macroeconomic risks. You can identify them. But relative pricing is not an ideal approach. It's sort of like it's really hard to find out the actual risks. So I step one step back, so that I do not consider the absolute pricing, but I consider some related asset prices and use that to figure out the asset that I'm interested. So you have to use the relatives price. And here, this relative pricing is mainly related to derivatives pricing, because derivatives, just like its name, it depends on the underlying assets, where the underlying assets usually say equities, bonds, or some assets that's relatively easier to price. So we use relative pricing for derivatives, and we use absolute pricing for equities. For bonds, actually, it can be used either absolute pricing or relative pricing. You can use either way. Of course, there may be some other assets that you want to find out the price, but more or less they can be classified into absolute pricing or relative pricing. So here in this course, we will focus on derivatives pricing and we'll focus on relative pricing. Okay? Okay, so that's the bigger picture. Then what is the relative pricing that will be used in this course? The core context, the core concept is no arbitrage pricing. So this is an important pricing approach that you will encounter from time to time. So you are supposed to learn how to use no arbitrage pricing to find out the price of a derivative. We will give you demonstrations in various different scenarios, and you will encounter this concept from time to time. Okay, so this is a no arbitrage pricing. If I want to use, okay, here we give you a general picture of it, and you understand that there are different assets and there are different asset pricing approach. It seems a bit messy, and it's covered different cases. But if I want you to use just the one formula to cover everything I discussed here, so that that formula can be applied to any of these assets and can cover both pricing approach. Is it possible? If I can do that, it seems to be a very nice way to summarize it, right? Can I do that? Or can you use one sentence to describe the pricing approach? Actually, you can do that. And there's a very another popular book. It's called Asset Pricing by John Cochrane. So if you want to do a PhD in finance, especially in asset pricing, then that will be a required textbook to read. So, but that book is too advanced for this course, so I did not list that here. But in that book, they actually tell us that you can use one universal pricing formula to do the price for everything as a pricing. This is the pricing formula. So this is the price, and you see this is the expectation. And M is a discounting factor. And X is a future payoff. So if I use one sentence to describe this formula, it is price equals the expected discounted payoff. Right? So you can actually use this universal formula to price all assets. And so this is also actually a formula that we will use for derivatives pricing. So price is always equal to expected discounted payoff. So the discounting factor takes the value of time, or take the time value of money into consideration. So you discount it back into the current time. And the future payoff, and also the discounting factor, it could be random, right? It could be, has some probability measures associated with it, or it could be random variables. So here we have the expected value to account for the risk. So you can see that this formula is just the expected value of the future discounted payoffs. Is it clear? Okay, so this is the general picture of this course. Now let's start with lecture 1. So I will use, so this is the lecture notes, right? So I will go through this lecture notes using this document camera and explain the concepts here. So in some circumstances, for the probability review, you can't find it in the prescribed textbook. So I guess you can find it in many different resources. Say, for example, the courses you have learned in introductory mathematical statistics or some other early year mathematical or probability courses. So I just give you a basic review. But later on, when I found out, okay, this section related to which page is on the textbook, I will let you know the page number or the section number. Okay, so then let's start with our lecture notes. So the first topic today is a review of probability. Okay, so here first I give you some motivation why we want to study probability. The reason is that as we earlier seen, so for the asset pricing or derivatives pricing, we really have to deal with the risks, right? So when we say risks, it just means uncertain. It really will be some uncertain future payoff or uncertain cash flows that we have to account for. So because we have to deal with uncertain events, so we use probabilistic models, which is a natural mathematical model to help us deal with those uncertain events. So that's really the mathematical basis for this course. So how to define or how to learn a probabilistic model, then basically it involves two steps. The first step is that we need to find a way to describe the uncertain outcome. We want to describe this. And secondly, we want to quantify the likelihood that an event will happen or not. So those two steps, we require these two steps to rigorously quantify the probabilistic model, or rigorously so that we can use mathematics to solve problems later. So let's focus on the first step. How can we describe an uncertain or a random event or a random outcome experiment, right? So the first concept is called sample space, and we give it a mathematical notation omega here. So what is the sample space? Let me give you an example. The easiest example is that you toss a coin. Then what are the potential outcomes? It's uncertain, right? When you toss a coin, before that you don't know which will appear, head or tail. You don't really know, right? So that's uncertain. What are the potential outcomes? Only two possibilities, head or tail, right? So you can put the outcomes here within the brackets. We call it a set. So it could be head or tail. Only two possibilities. And I include every possibility here. This is your sample space. So you can see what are the features of the sample space. The features are, firstly, it has to be mutually exclusive. If it's head, it can't be tail. If it's tail, it can't be head. It has to be mutually exclusive. And secondly, it has to be collectively exhaustive. That means it has to include all the potential outcomes. It can't leave any other possibilities outside outcome. So it can be head or tail, and it can only be head or tail. There's no other possibilities. If there is, then you should put that within the outcome. So it has to be collectively exhaustive. So that's are the basic features of the sample space. And then I will give you a chance to write down the sample space. Here, I want to toss a coin twice. Now, write down what are the sample space yourself. What are the potential outcomes? Remember, it has to be mutually exclusive and collectively exhaustive. Yes, yes, so it's have to be H, 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 T, T, H, T, T, right? That's all, thank you. So that's all the possibilities. That is sample space. And then after that, it seems that now we have completed the first task that we describe some potential uncertain outcome using sample space. What's the next step? We want to assign probabilities in it. We want to assign a likelihood. Can we do that directly? Say, can we assign a probability of each of these outcomes? It seems to be possible for this case because they are all discrete. Right? For the perfect, say, coin, the probability of having head or tail is like, you can say it's a half, right? Half, half. But it's not always the case. If it's a continuous, if the sample space is continuous, for example, if it's a unit square, 0 to 1, for example, it's a continuous space. And you can draw outcome. Say, you can put a point here, which has infinite accuracy here, just the dot within this square. What's the probability of having this dot? It's 0. So although it seems that after defining the sample space, you can directly assign probability there, but it's only for those discrete outcomes. This is continuous. Those dot points will all have a probability of 0. So that makes the task difficult. So we can't just assign probability directly to those outcomes within the sample space. So we define another concept. To solve this problem, we define the events. Events are usually denoted by A, B, those capital letters, and they are defined as subsets of this sample space. They are the subsets. For example, it could be, if it's a continuous case, you can circle an area that's a subset. So if this is omega and this is A. And for the discrete case, let's go back to our first example again. If you toss a coin, then you can define the event as having a head, or B as having a tail. Right? You can define events as subsets of the omega. Or if this exercise 2, when you toss a coin twice, you can define and say C events as having head, tail, which I describe the events as the first toss results in the head. The first toss results in the head, then this is the event, which is C. Right? So basically, the events are subsets of omega. And so you can see that it can include every single outcome, but it can also include some combinations of these outcomes. It can be an empty set. It can also be the entire omega, the entire sample space. So it's just the subsets. This is events. Okay, now with the help of events, can we assign probabilities to the events now? It's possible, but we still need some other definitions, because we know that events are subsets of omega. But to make the probability measure consistent with our common sense, what is our common sense? Our common sense is that if two events are disjoint, completely disjoint, then we should make sure that the probability or the likelihood of one event happen or the likelihood of the other event happen, if you want to consider the joint, if you want to consider the probability that either this event happen or this event happen, then you should be able to use some mathematics to calculate that. Say the probability of A plus the probability of B. Right? So you should be able to use some mathematical operations to describe the events. So that means we have to make sure that the sets of the events have to satisfy some good properties, so that when we define the probability measures, those operations will be consistent with our common sense. Then we need another concept, sigma algebra, or the sigma field of events. So it's basically a collection of events so that we can make sure it has some good properties. And it's usually denoted by this F. So what are the properties or the requirements for a sigma, for the sigma field of events, for this collection of events to have some good properties? They are basically, we require three properties. The first one is that the sample space, the omega, belong to this algebra. And use this, you can derive that. We can derive that later. So this is basically the sample space belong to this collection of events. And secondly, if the event A belong to the sigma algebra, then we have the complement of A also belong to the sigma algebra. Right? So A is like the event happened. And then the complement of A is the event doesn't happen. So this both, if an event belongs to this, then the complement has to belong to, or we can call it closed-ended complement. And the third one is if A1, A2, a sequence of events are in the sigma algebra, then the union of these events also belong to this sigma algebra. Always say it's closed under countable unions. This is closed under complement. This is a definition of a sigma algebra. So now we have defined the sample space, we define the events, we define a collection of events, which is called the sigma algebra, as long as those events within this sigma algebra satisfy these three properties. And then finally we can define the probability measure. It's usually use capital P to denote the probability measure. So we usually say a probability measure of an event. Right? So probability measure is well, in general, it's just a measure. Right? But we call it probability measure because that's consistent with our understanding of an event, the likelihood of the event happening. So we have the requirements of this probability measure. The first one is the probability has to be bounded between 0 and 1 for all events belong to this sigma algebra. So in other words, the probability measure P is defined on this sigma algebra. Okay? So for all events belong to the sigma algebra, a collection of events, then you can assign probabilities on these events. And these events, the probability has to be between 0 and 1. This is to be consistent with our common sense, right? So that we understand if it's a probability is 1, it will definitely happen. Probability 0, it definitely will not happen. And somewhere in between, we know the likelihood it will happen, right? So we define it in this way to be consistent with our common sense. And then when it will be 1. So the probability of the sample space is 1. And the probability of an empty set is 0. And any other events will be a number. The probability of any other events will be a number between 0 and 1. And the third one is, we call it sigma additive. And because of the good properties of the sigma algebra, so we can see that this probability measure has a sigma additive property. That means if I put it in a simple way, I'll firstly give you a simple case. For example, if A and B, we only consider 2 events. So I use this is A intersect B. A intersect B is, say, empty set. These 2 sets are completely disjoint. then the probability of A union B equals the probability of A plus probability of B. Right? So if I make it more general, then I can put it as if A1, A2, a sequence of events are disjoint. This is two events. Now I generalize it to more events. If those events are disjoint, and they, of course, they have to belong in the sigma algebra. As I mentioned before, the probability is defined on the sigma algebra. So we have the probability of the union of all these events equals the summation of all these events. This is just a natural generalization of the two sets case. And we won't have it because this is consistent with our common sense. Say you have two, this is your omega, and then you have two sets A and B. Right? These have no intersection, so we say the disjoint, they are disjoint. The intersection is empty. So the probability of A union B, it happens either at A or B, will be the probability, the summation of these two. Okay, now we summarize what we have described earlier using the probability space. So the probability space mainly have three elements: sample space, sigma algebra, and the probability measure. Okay, so this is all the sets includes all the potential outcomes, and this is a collection of events that satisfy three properties, and this is a probability measure defined on the sigma algebra. Okay. The reason we need this, the middle one, the sigma algebra, because only in this case we can have the probability measure satisfy these three properties. And you can see that from this one you can derive. You actually can derive. There are different ways to set up, say, the property of this one. So say you can put down different requirements. You can also say phi belongs to the sigma algebra. You can replace the first one by the phi belongs to 1, because you can use 2 to derive the omega or the empty side belongs to 1. So you can actually replace this one by some other properties, as long as they are, can derive one another from the others. So, and you can also try yourself. You can derive some other properties based on these three basic axioms. Questions? Okay, I think now we have a 5 minutes break, and we'll be back around 12, 8 past 12. lecture today. So the next concept, we have defined the probability space, right? We understand what is a sample space, sigma algebra, and the probability measure. Then the next one we are going to discuss is called random variable. Random variable, so you probably have already come across this concept in different courses. It can be discrete, it can be continuous. Here we'll give you a more rigorous definition of a random variable. Random variable is nothing but a measurable function. It's a function. It's from the sample space to the real line. So we call the random variable x. It's just a function from the sample space to the real line. And the definition is that we put it on the lecture notes. So it's a function on omega such that there's a set, the set of the small omega, which satisfy that the x omega, the function of x, the function of omega is smaller or equal to small x. So this set belongs to the sigma algebra. It's an event in this sigma algebra for all x. Then we call this is a random variable. This is x. This is a formal definition. So you can see that this definition can map the sample space into the real line, so that when you have when you define, say, you have an omega, small omega from the sample space, and you put a function on it and make sure that this value is smaller or than equal to x. And then this all possible omega is an event within the sigma algebra. So you can, in other case, so this can be seen as this x omega smaller or equal to x. So that means it's from negative infinity to x. And for all omega within the sample space, for all small omega within the sample space that can satisfy this, you can get a collection of this omega, right, that satisfy this. Then this have to be an event within the sigma algebra. If that's the case, then this is a random variable. Okay, so this is a formal definition of a random variable. So this is just a measurable function that's mapping from the sample space to the real line. And you can see that within the definition, we also require it's based on the sigma algebra, so that it's measurable. So in other case, we can assign probability measures on it. And then after this formal definition of random variable, we give you some specific examples. Say discrete random variable. Right. So for the discrete, it means this random variable can have specific values, that's x1, x2, and you can assign probabilities here. When x equals x1 or x equals x2, say I equals 1 or 2, then you can assign a probability on it. We call it, say, a probability mass on it. This is a probability when this random variable equals xi. Here, of course, we have pi is bigger than or equal to 0, and the summation of all pi is 1. So this is based on the properties of the probability measure, right? This is a discrete random variable. And then the next one is, okay, so let's give you an example of this discrete random variable. Can you give me an example of discrete random variable? What's the simplest discrete random variable? Say a Bernoulli random variable, for example. Bernoulli random variable, right? So for the Bernoulli one is that x can only be either of these two values, 1 or 0, each with a probability. So it's with probability 1, with probability p to be 1, or with probability 1 minus p to be 0. This is a Bernoulli random variable. This is a discrete random variable. And then the next concept is the probability mass that we have just briefly mentioned. So for discrete variable, we have this PMF, probability mass function, because for discrete variable, we can assign probability for each individual values, and we call it probability mass. And we can put it as the probability of x equals xi, and this is the probability mass, right? But for continuous variable, we won't be able to do that. Each of for the individual elements, it's just to get a probability of 0. So we will have a probability density function. And then let's talk about the continuous variable here. We talk about absolutely continuous random variable. So we won't, just to make it easier, we won't consider, say, continuous random variable with some potential jumps or almost surely continuous. We just consider a very straightforward case, absolutely continuous random variable. So we put it as, we'd say we define an absolutely continuous random variable on A and B closed. So we can define a probability that X is bigger than A or smaller than B. And then that is the probability that we can use the random variable definition that we have to make sure this is the probability of a collection of omega that X omega is bigger than A, smaller than or equal to B. Right? So this is on the real line. Right? This is on the real line. And this is on the omega sample space. Right? So you can see that we have to, this probability, we can map back to the sample space using the random variable definition. Right? So this is a probability of a collection of outcomes, where the outcome satisfies that when you put a function x on this outcome, it has a value between A and B. So this is absolute continuous. And if you know the probability density, you can calculate this by putting an integration. Okay, so fx here is called this is the probability density function. And we call it PDF. So this is absolutely continuous random variable and how to calculate probability based on it. And then the next one is cumulative distribution function. CDF. This is defined as, say, here I put a subscript capital X to make sure to let people know that this is the function related to this random variable X. And here within the brackets, I put a small x that has the meaning that I want to calculate the probability that when this random variable is smaller than or equal to small x. So we use the small x to define the values and the capital X to define the random variable. Right, so this is a cumulative distribution function when the probability is smaller than or equal to x. And then we have two versions, either discrete or continuous. So for the discrete, if x is a discrete random variable, then how to calculate this cumulative probability? because x can be specific values, so we just put xi smaller than or equal to x, and then this is the probability of I. And then for the continuous one, we have to use the integration from negative infinity to small x, and then this is using the density function to draw an integration of it. So basically, for the discrete random variable, you can use the summation to calculate the cumulative distribution function. And then for the continuous random variable, you have to use the integration. Is it clear? I'm sure you have learned all of this in the previous courses, so this is just a revision. And then the next concept is expectation. For the expectation, we also have two versions, the discrete version and the continuous version. So the expectation of a random variable x, if it's discrete, then we have, it is the summation of all possible x when this is x times the probability of the random variable equals to this small x, right? This is the expectation when x is a discrete random variable. For x as a continuous random variable, then we have to do an integration from negative infinity to infinity, where we have x times f x, and then dx. So this is an integration. This is an integration operation. So we have to use the integration to calculate the expectation of a continuous random variable, right? With all the possible x multiplies probability density. Any questions? Then the next concept is, so what if we have another function g? So g is from real line to real line. So this is a function. So how can we calculate the expectation of a function of x? Right? Again, we can apply the previous two, whether x is discrete or continuous. So if it's discrete, then this is the summation of all possible x. We just replace x by gx, and then calculate the probability. X equals x. But if it's continuous, again, we use integration, but replace x by gx, and then dx. So this is x discrete, and this is x continuous. Is it clear? So this is how we calculate expectation of a function of x. Okay, so actually now we only discuss a univariate case where we only consider one random variable at a time. So now what if we want to consider some multivariate distribution, or consider two random variables together? Then we will need the concept of joint distribution. So we consider two random variables, x and y. They all are on the same sample space omega. Right? And then how can we define their joint distribution? So we can say x and y is defined on R squared. This is a two-dimensional space. So how can we define the cumulative distribution function here, we got two random variables x and y. Say, then we can define this notation, the CDF of these two random variables, as a probability that random variable x smaller than or equal to x and random variable y smaller than or equal to small y. This is a joint distribution. And then we define the marginal distribution. So the marginal distribution is that although we have two random variables, but we only consider one of them. So we define it as a marginal distribution. So we can see it's defined as, again, we go back to the joint CDF, and this is x, where for the y space is infinity. That means y can take any values. And then that is the probability of x is smaller than or equal to small x. Similarly, we define the marginal distribution of y by using the joint CDF, that is x can be any value, but y has to be smaller than or equal to y. This is the probability of y is smaller than or equal to y. And this is the marginal distribution of these two in the bivariate case. And then the next concept is independence. Independence is a very strong concept. And so I want to remind you that independence is different from uncorrelated. Okay, independence is different from uncorrelated. It's much, much stronger than uncorrelated. So uncorrelated in the simple linear, under the simple linear, say, form, then they are equivalent. But independence is much stronger. So if we say x and y, two random variables, they are independent. So we define, we use a sample space to define. So x is when omega is a set of omega that x omega is smaller than or equal to x. So this belongs to the sigma algebra, right? And then for y, the sample space version is that we define another omega that's y omega is smaller than or equal to y. If this belongs to the sigma algebra, then that's y is random variable. So we can have these two definitions in the sample space version, mapping back to the sample space. And then we can see that if we say x and y, they are independent, then these two mapping back to the sample space, they are also independent. So I just use this one to denote independence. If x and y are independent, then the sets within the sample space are also independent. And for the independence, we do, if x and y are independent, then we have some properties of the probabilities. For example, x and y. So this is their joint probability, right? This is the joint probability of, let's say x and y, they are the discrete random variables, and they are independent. Then we can put the probability of x equals small x, the probability of x equals small x, y equals small y equals the product of their two marginal probabilities for any x and y. So this is the property of the independence. And the next one is if it's continuous random variable, then we can put down the density function. So the density of x, the joint density of x and y equals the product of the density of the marginals. So this is x for all x and y. You can see under this independence condition, then the probability mass and the probability density will have these properties. I guess you can derive other properties under this independence if you want. And then the next one is conditional probability. Say, here we also consider two random variables, x and y. Let's start from a discrete case, if they are discrete random variables. And we assume that the probability of y is always bigger than 0. So it can't be 0, for example. Then we can define the conditional probability that say that random variable x equals small x conditional on random variable y is equal to small y. And then this is a conditional definition of conditional probability. Conditioning on y equals to small y, then the probability of x equals to small x. How to calculate that? You can use the joint probability divided by the probability of y equals 1. And then similarly, when x and y are continuous random variables, you can have a similar formula for the density function. The density of x conditional on y equals the joint density of x equals x, y equals y, conditional on this marginal density of y. So this is a conditioning, right? So this is a conditional probability. So you can derive the conditional probability or the conditional density using the joint probability and the marginal probability. Clear? And the special case for this conditional probability is that when x is independent of y, then you can see that when it's conditional on, then because for the numerator, if these two are independent from what we have derived, the numerator can be written by the product of these two. And if you replace this joint probability by the product of these two in each of these two formula, one of the elements can be cancelled out with the denominator. So you can see that if these two are independent, then this conditional probability is just the probability itself. You can get rid of the conditioning here. Similarly, this one just equals fx. This is a special case when they are independent. Okay, that's all about the probability. As I said before, I'm sure you have learned all of this. This is just a quick review of these basic concepts so that later on our more rigorous mathematics will all be built on these foundations. If you find yourself a bit unclear of anything, you can maybe you can review some of your earlier courses, introductory mathematics or some other, say, introduction stochastic process. Okay, then the next topic for today is to review forwards and futures. So now we really start to look at derivatives pricing, and the first derivatives we want to look at is forward and futures pricing. So for this part, I think the most of the material will be very similar to what you have learned in derivatives or some other courses that have a derivative section. They will be very similar because for this part we don't require. It's not continuous time finite. It's mainly used no arbitrage pricing theory, and we do not require the Brownian motion or more difficult mathematical concepts. So this material should also be regarded as a review because I'm sure you have learned this in earlier courses. So the review is about forwards and futures pricing, and well, the key takeaway is to be familiar with no arbitrage pricing. Although the mathematics here is relatively simple, but the concept is very fundamental. It's very important. So we will use no arbitrage pricing to use this revision to get familiar with no arbitrage pricing. And before that, let's make some assumptions. Here, I want to remind you that especially later on when you got a job in the industry, whenever you want to apply some model, first ask yourself, are you comfortable with those assumptions? Or have you already understand the impact of those assumptions? It's very important. All models are wrong and all models require assumptions. So we have to be careful with that. Be cautious of using models if you are uncomfortable with those assumptions. So the assumptions that in this section is, firstly, no transaction costs. Uniform taxes. Basically, we will not consider tax. Unlimited lend or borrow as the interest rate R. R denotes the interest rate. And then we assume this is a very mature and competitive market, so arbitrage opportunities will exploited very soon. And then unlimited short selling. So we set up a very ideal context so that we can get rid of all those noises in the real world, and we only focus on the core part of the pricing. But when it comes to reality, you may want to modify the formula so that it can really take the actual reality into consideration. But because the objective of this part is to really understand the no arbitrage pricing, so we don't really need to care about all those other factors. Right? So because we want to focus on this pricing part. Okay, the first section is about forward pricing with no income. Do you still remember what is a forward contract? A forward contract is saying that, say, you initiated a contract at time small t, and the contract says that you can deliver the underlying asset at time capital T. This is the delivery time. This is the time that the contract is initiated. And then this is a forward contract where there are two options, two positions, a long position, a short position of the contract, right? And then we also assume that there is a risk-free interest rate. R is the risk-free interest rate. And we also assume that because the contract is initiated at time t, say underlying asset is an equity, just as an example, or any other asset, you can observe the asset price at time t. So this ST is the spot price of the underlying asset. At time small t. And the question is, can you tell me the forward price? So here, I want to be careful that here I use the subscription
small t, this means this is a forward price initiated at this time. But this forward price will be transacted at time capital T. Okay, this will be the transaction price at time capital T, but initiated at time small t. So this is FT. And what is the forward price of this contract? Initiated at time T will be delivered at capital T. What is the forward price? Can you try to solve this using no arbitrage pricing? Remember, right? We have to use no arbitrage pricing because this is a review section. So I want to give you, say, 2 minutes to think about what is a strategy to find out FT using no arbitrage pricing. I'll give you a chance to think about yourself first. Okay, I'll give you some hints. For this type of question, there are actually, you can find different ways to solve it. One typical way is that if you want to find out this price, you can create two portfolios, portfolio 1 and portfolio 2, where you make sure that this portfolio, for example, they have exactly the same payoff at time capital T. This is say payoff. This will give you payoff 1, and this will give you payoff 2. And then because these payoffs are exactly the same, one to the other same, then based on the no arbitrage pricing theory, you should have the same price at time small t. The price 1 and the price 2 should be equal. Otherwise, there will be arbitrage opportunities. So this is a very typical way to solve this type of problem. This is method 1. Method 2 is that if you can figure out, say, for example, if you remember that this price actually can be written as ST, the spot price, accumulated to capital T based on risk-free interest rate. Say, in some case, you just remember this formula very clearly. And so this is just, okay, it's just accumulated price of the spot price with the risk-free interest rate. But then you forgot how you derive this. Then you can use another method called is by contradiction. Right, so you believe this is the correct answer. Then you can derive it can't be FT bigger than this amount. It can't be that. On the other hand, it can't be FT smaller than this amount. It's also false. Then by because either this way or this way, you will derive contradictions. And then you can conclude that it has to be equal to this price. Otherwise these two possibilities will all lead to contradictions. Then you can also prove that. So later on, in this section, I will give you examples of both first and second method. So in this case, I will give you an example of the second case and leave it to you to think about how to create two portfolios to solve this problem. But for later examples, I will use the first case. Okay? Okay, let's consider the second case. Let's say you remember this is a correct formula, and then you want to prove that this is the correct forward price by contradiction. How to do that? So firstly, we suppose FT is actually bigger than this amount, then the right-hand side, then we derive contradiction. Capital T minus small t. Right? So if this amount is this one, how can we derive contradiction by no arbitrage? Assume that in the market, no arbitrage. If you can derive that, if this is the case, there is arbitrage opportunities, then you derive the contradiction, right? So how can we derive that? Say at time small t, we create a portfolio which includes, firstly, a short position of the forward contract. What does it mean by short position? Short position means you have to sell the underlying asset by the maturity. It means sell. Long position means you have to buy the underlying asset at the maturity, at the delivery date. Okay, so your portfolio has a short position, and then you also borrow ST and buy the stock at time t. Because you have to sell the underlying asset. So this is to make sure that you have that in hand so that you can sell it later. So you borrow ST and you buy the underlying asset. And then you're in the short position so that at time capital T, you can sell it. So that's the idea. And then how about at time capital T? What you get? Then because you're in the short position, you sell the underlying asset, sell the stock. What you get? You get the forward price because you are on the contract, right? The contract has the listed forward price FT, which should be the transaction price. So you receive FT, the forward price. And how about the other part? You borrowed ST and you buy the stock and hold it. And how much should you pay back? You should pay back not only ST but also the interest. So you should pay back ST and with accumulated risk-free interest rate. Because we assume that unlimited lend and borrow at the same risk-free interest rate. Right? So we borrow something, when we pay back later, we have to pay back both the principal and the interest rate, which is this one. Okay, then let's sum up. How's the opposition? So you can see that because FT is bigger than this amount, then what's your ultimate payoff? At time T, you don't have to pay anything. Right? So at time T, you just borrow something and buy the stock, and then at time capital T, you sell the stock and pay back. Then your ultimate position is FT that you received minus the amount that you pay back. So this is at time T, your position. Because FT is bigger than this, so this is bigger than 0. What does that imply? This is your risk-free profit. This is an arbitrage opportunity. You get something without any loss, right? So this is a risk-free profit. it can't be true because we do have the assumption that there's no arbitrage opportunity. So there is a contradiction. So it doesn't hold. So this assumption doesn't hold because it will lead to a contradiction. So this assumption doesn't hold. Okay, so we just proved one side. How about the other side? Suppose ft is smaller than st. Can we derive another contradiction? It's very similarly. So here at time t, so you can see that my objective is to derive some risk-free profit so that it's an arbitrage opportunity. So if ft is smaller than this amount, I will change my position to the long position. That means at the maturity capital T, I will have to purchase this because the forward price is small, so I want to purchase it so that I can potentially get an arbitrage opportunity. So now you got the long position of this forward contract. And then, because now this underlying asset has a bigger price, right? So the other position is that you short sell. You short sell this underlying asset, so the stock, for ST. And invest ST with a risk-free interest rate at time T. And you have the risk-free interest rate R. So you short sell the stock and invest it at the risk-free interest rate at time T. Okay, and then how about at time capital T, what you will get? At time capital T, you have to, so for the long position, right, remember we have to buy the underlying asset. So we pay the forward price FT and close the position. Right, so we buy the assets, we pay this amount, and we got the stock. And how about the other one? Because we got the stock, and then we short sell the stock, so we can pay back the stock. And then what we get is the ST grow to ST times ER capital T minus small t. Because we invest this ST at time T, so you can, this amount grow to this amount at time capital T. And then what is the ultimate payoff of this position? So you can have that. You have ST. You receive this amount and you pay this amount. So in total you have achieved this one minus FT. So because of the inequality, the assumption you made at the beginning, this amount have to be positive. Again, you earn the risk-free profit. And that means this one doesn't hold. And because this is a contradiction. Right? Because you should not earn any risk-free interest rate. So, well, based on these two steps, you can see that FT can't be smaller and can't be bigger than the accumulated value of the swap price. So you can make your conclusion that with 1 and 2, you can see that FT has to be equal to ST times ERT minus T. Right? You can achieve this solution. Again, I encourage you to consider a different way to find out the price by considering two portfolios, and which have the same payoff, and then it should have the same price at the beginning. You can derive the same answer. Is it clear? Any questions? Okay, the next topic is